Right now, your phone is running on 15 billion switches. None of them have any moving parts. Not gears, not heated wires, not glass tubes. Solid crystal, and nothing moves. The device that made this possible didn't just make computers smaller, it changed the branch of physics computers run on entirely. One machine filled a gymnasium, the other fits in your pocket. Both are computers, the physics between them changed completely. Two physicists at Bell Labs cracked it in 1947. Their names were Bardeen and Brattain. They spent 2 years failing. The device they designed on paper worked perfectly. The one they built did nothing. Two men, a crystal the size of a fingernail, and a physics problem nobody could explain. The machines of 1945 ran on vacuum tubes, glass bottles that worked by boiling electrons off a heated wire at 250 degrees Celsius. That heat wasn't a design flaw, it was the mechanism, and there was no way around it. But how do you build a switch with no heat, no vacuum, no moving parts, when every prior experiment says the physics won't allow it? Let's start with what everyone was using. Inside a glass vacuum chamber, a wire heats to 250 degrees. Free electrons stream across the vacuum. A grid electrode controls the stream. Small signal in, large signal out. It worked. Radio, radar, the first computers, all built on vacuum tube physics. But that physics came with a cost that couldn't be engineered away. Every tube ran at 250 degrees continuously. Filaments degraded, glass seals cracked. The average tube lasted between 1,000 and 2,000 hours, which sounds manageable until you build a machine with 18,000 of them. ENIAC, 1945, broke down on average every 2 days. 1,800 square feet, 150 kilowatts of power, and it still broke down every 2 days. Not from poor engineering, from the physics of running 18,000 heated filaments simultaneously. There were technicians whose entire job was walking those rows with a flashlight, hunting for the one failed tube in 18,000 that had crashed the machine. Every calculation was a race against the next failure. Most races were lost. First response: build a better tube. Oxide-coated cathodes, cooler, longer lasting, maybe 3,000 hours instead of 1,000. The machine still broke down every few days, because making the same physics more efficient doesn't change the physics. The heat was still there, the fragility was still there. They had improved the mechanism, they hadn't changed it. Second approach: crystal rectifiers. Current flows one way, blocked the other. No heat, no vacuum. But a rectifier cannot amplify. Output always weaker than input. For a computer, a dead end. Approach 2, eliminated. The third approach was theoretically correct and the one that failed most completely. Shockley applied a voltage above a semiconductor crystal. It should have controlled a current channel with no heat, no vacuum, no moving parts. The physics on paper was sound. Shockley built it. It did absolutely nothing. 2 years, zero amplification. Correct theory, completely unusable device. Nobody could explain why. Here's what went wrong. Semiconductor crystals aren't clean at their surfaces. The atomic lattice terminates in a layer of broken chemical bonds. Those incomplete bonds act as electron traps. When Shockley's field tried to push charge carriers toward the surface, the traps captured them first. The field effect was neutralized before it could do anything useful. His device worked perfectly in theory and failed completely in practice. John Bardeen spent most of 1946 and 1947 working on nothing but the surface state problem, the obstacle that wasn't even supposed to be the main problem. Bardeen's insight: stop fighting the surface. Inject carriers directly into the interior of the crystal. A tiny current at one contact controls a much larger current at the other. The amplification happens deep in the lattice, bypassing the surface traps entirely. December 16th, 1947. They connected the germanium device to a microphone and a speaker. The voice that came out was louder than the voice that went in. It worked. The modern transistor is Shockley's bipolar junction transistor, running on the same physics Bardeen identified. One step at a time. Step 1, pure silicon, every electron tightly bonded, no free carriers, 0 current flows. Step 2, add a trace of phosphorus, 1 extra electron per atom free to move through the lattice. N-type silicon, it can carry current. Silicon grown so pure that 1 misplaced atom in a billion matters. Step 3, dope with boron. Boron leaves an empty slot, a hole. Neighboring electrons fill it, making the hole itself drift. This is P-type silicon. Step 4, the sandwich. N-type emitter, thin P-type base, N-type collector. 3 layers. The thinness of that middle layer is the entire secret. 3 leads, a metal cap the size of a pencil eraser. Step 5, nothing applied to the base, both the junctions are blocked. A depletion zone forms, swept clean of carriers. Switch open. Step 6, apply a small current to the base. Carriers are injected into that thin P-type layer. The depletion region narrows. The barrier starts to open. Step 7, the base is so thin, most carriers pass straight through before they recombine. 1 unit in, 100 units out. A small signal governs a large one. The gain is what makes a computer possible. Each transistor stage drives the next. Step 8, wire 2 transistors so both must switch on for current to flow. AND gate, true only when both inputs are true. The first building block of every processor your phone has ever run. Bell Labs classified the result for 6 months. The announcement in June 1948 was buried by most newspapers, a small item about a semiconductor amplifier. Shockley filed his own patent for a superior junction transistor 2 weeks later, the design we still use today. All 3 received the Nobel Prize in 1956. Shockley spent most of his acceptance speech taking credit for the discovery that had happened without him. So why was Bell Labs, a telephone company, funding semiconductor physics? AT&T's transcontinental network ran on vacuum tube amplifiers. Every 50 miles, the signal degraded, a repeater station amplified it and sent it forward. 15,000 tubes per transcontinental route. The weakest tube was always failing somewhere. The entire network dropped when one did. Hundreds of isolated stations, a maintenance infrastructure built to manage one physics problem that couldn't be solved. AT&T wasn't trying to build a computer. They were trying to stop their phone calls from dropping. The transistor was a solution to a telephone problem, one that happened to make the entire information age possible. Meanwhile, ENIAC was 1,800 square feet, enough power to dim the neighborhood, and still crashed every 2 days. The vacuum tube era wasn't a stepping stone, it was a physics ceiling. You could not engineer away the heat. The heat was the mechanism. The only way forward was completely different physics. More tubes, bigger racks, same ceiling. The problem needed different physics, not more of the same. It needed 3 physicists, a germanium crystal, and a problem nobody had thought to study until it was the only problem left. The transistor Bardeen and Brattain built was roughly the size of a fingertip and had to be assembled by hand. A decade later, engineers put multiple transistors on the same crystal. Jack Kilby, Texas Instruments, 1958. The integrated circuit. Transistor connections no longer soldered by hand, part of the same crystal. Gordon Moore observed in 1965 that transistor counts doubled every 2 years. The industry organized itself around it. 1971, 2,300 transistors. 2024, 25 billion. Chip the size of your thumbnail. Same physical chip area, 58 million times more transistors. The machines that print them cost $150 million each, features 2 nanometers wide, 40,000 times thinner than a human hair. The transistor in your phone is a MOSFET, exactly the field effect device Shockley tried to build in 1945, the one that did nothing. His theory was right. He was just 60 years ahead of the manufacturing process that could execute it. Same physics, 75 years of material science to make it work. Every data center, every AI model, every financial transaction, same principle Bardeen identified in 1947. A small signal in, large signal out. Everything that followed. Bardeen won the Nobel in 1956 for the transistor. He won it again in 1972 for a completely different discovery, the only person ever to win it twice in physics. Every computer, every phone, every line of code, all of it, a thin sandwich of doped crystal, a gate that opens and closes. The transistor didn't make computing faster, it made computing possible. Murray Hill, New Jersey, December 16, 1947. Everything that followed.